Welcome to Understand the Math. This video is part of a series of videos on linear algebra and its applications and covers the first part of section 1.9 on the standard matrix of a linear transformation. I'll teach you how to find the standard matrix of a linear transformation, explain what it is geometrically, and then walk through 3 example problems where we'll find the standard matrix for a linear transformation and use it to find transformations of vectors. Be sure to check out the link below for free guided notes that you can highlight and fill in as you watch this video. The standard matrix of a linear transformation contains transformations of vectors that are called standard basis vectors. These vectors are just unit vectors with a magnitude of 1 that point along one of the coordinate axes. In R2, there are 2 standard basis vectors. These are E1, which is equal to 1, 0, and E2, which is equal to 0, 1. E1 is the same as I hat, which you already may be familiar with, and E2 is the same as J hat. E1 is the standard basis vector in the direction of the x-axis, and E2 is the standard basis vector in the direction of the y-axis. Any vector in R2 can be written in terms of these standard basis vectors. For example, we can write xy as x times the vector 1, 0, plus y times the vector 0, 1, and then this is just x times E1 plus y times E2. This is just the same as writing x times I hat plus y times j hat. Likewise, any vector in Rn can be written also in terms of standard basis vectors. Our vector x is equal to x1, x2, all the way down to xn, and we can write this as x1 times E1 plus x2 times E2, all the way up to xn times en. When we're working with linear transformations, if we know how the standard basis vectors transform, we'll be able to determine how any vector transforms. We're now going to use these standard basis vectors to find the standard matrix for a linear transformation. A standard matrix for a linear transformation is just a way to describe linear transformations algebraically. If we have a linear transformation T that maps vectors from Rn to Rm, we can write T of x as A times x. Multiplying vector x by A transforms vector x into vector T of x. Our matrix A is called the standard matrix for a linear transformation because it transforms vector x into vector T of x. Matrix A is equal to the transformation of E1 in its first column, the transformation of E2 in its second column, all the way up to the transformation of E sub n in the last column. To understand the standard matrix for a linear transformation graphically, let's revisit the example that we looked at in section 1.8. We had a matrix A, we multiplied it by a vector x, and then we got a vector T of x. In the diagram on our right, we can see that we have a vector x that transforms into a vector T of x. This transformation happened because we multiplied x by matrix A. Our matrix A was the matrix 1, 3, 2, 3, and we now know that that's equal to T of E1 and T of E2. T of E1 is the vector 1, 3, and T of E2 is the vector 2, 3. In our diagram below, Our green vectors are E1 and E2, and our purple vectors are the transformations of these green vectors, and they're equal to T of E1 and then T of E2. Our vector x is pictured down here in pink, and that vector is equal to -1, 2, and we can think of this vector as minus E1 plus 2 times E2. In the same way, we can think of T of x as a linear combination of T of E1 and T of E2, just like x was a linear combination of E1 and E2. Let's see what this looks like. We have T of x is equal to a times x, and we can write this as -1 times our first vector plus 2 times our second vector. This shows us that T of x is -1 times T of E1 plus 2 times T of E2. Geometrically, we can envision T of E1 and T of E2 as a new coordinate system. That coordinate system is shown by our dotted purple lines in our figure. And then we can envision T of x as x in that new coordinate system. We're now going to walk through 3 example problems where we'll find the standard matrix for a linear transformation and use it to find transformations of given vectors. In our first example, we're given T of E1 and T of E2, and we're asked to find the transformation of a given vector x. Suppose T is a linear transformation that maps vectors from R2 to R2 such that T of 1, 0 is equal to 2, 5, and T of 0, 1 is equal to -1, 6. We're asked to find the image of 5, 3 under our transformation T. Let's begin by noticing that 1, 0 is our E1 and 0, 1 is our vector E2. We're going to set x equal to the vector 5, 3, and then we'll find T of x, which is the image of x. Sometimes the hardest part of these problems is understanding what you're given and just trying to figure out what you actually need to compute. Our T of x is equal to a times x, and we know that a is equal to T of E1 and then T of E2. Looking up above, we can see that T of E1 is the vector 2, 5, and that goes in our first column. And then T of E2 is the vector -1, 6, and that goes in our second column. We can now compute T of x. It's equal to our matrix A, which is 2, 5, -1, 6, times our vector x, which we were given as 5, 3. Let's now compute this matrix vector product. It's going to be 10 minus 3 on our first row, and then 25 plus 18 for our second row. This gives us an answer of 7 and 43. This vector 7, 43 is the image of vector 5, 3 under our transformation T. Let's now look at our second example. This is a very difficult example, but I'll walk you through it step by step. In this example, we're given the transformation of a vector u and the transformation of a vector v, and we're asked to find the standard matrix of the transformation. In our problem, we have a linear transformation T that maps vectors from R2 to R2, and we're given that T of 1, 1 is 1 minus 2, and T of 2, 3 is -2, 5. And then let's highlight that we're asked to find matrix A. Let's begin by labeling the vectors that we've been given. Let's label the 1, 1 as U, and we'll label the 2, 3 as V, and then our 1 minus 2 is our T of U, and our minus 2, 5 is our T of V. Let's now talk about what we have to do. To find A, we need to find T of E1 and T of E2, because that's the definition of A. To find T of E1 and T of E2, we're going to write U and V in terms of E1 and E2, and then take their transformation. I have our problem broken up into steps. Our first step is to write U and V as a linear combination of E1 and E2. Let's go ahead and do that. We'll start with U and write that U is equal to C1 E1 plus C2 E2. Our vector U is given up above as 1, 1. And we're going to write this as C1 times our E1, which is 1, 0, plus C2 times our E2, which is 0, 1. You can see by inspection that this is just going to be equal to 1, 0 plus 0, 1. And C1 and C2 are both equal to 1. So our vector U is E1 plus E2. Let's do the same thing for V. V is going to be C1 E1 plus C2 E2, and our C's are going to be different. Our vector V up above is 2, 3. And you can see without writing down the C's that this is going to be equal to 2 times 1, 0 plus 3 times 0, 1. So our vector V is just 2E1 plus 3E2. Our next step is to calculate T of U and T of V. To calculate T of U, we'll write down what we just found in step 1, that U was equal to E1 plus E2. Now we're going to take the transformation of both sides. On the left, we have T of U, and on the right, we have T of E1 plus T of E2. Looking up above, we can see that T of U is 1 minus 2. So we can say that T of E1 plus T of E2 is equal to the vector 1 minus 2. Now let's do the same thing for V. In step 1, we found that V was 2E1 plus 3E2. Now we'll take the transformation of both sides. T of V is 2 times T of E1 plus 3 times T of E2. Let's now look back up above, and we see that T of V is equal to minus 2, 5. So this expression is minus 2, 5. I'm going to highlight these two equations. That's our first equation, and this is our second equation. We'll label this one as equation 1 and this one as equation 2. We have two equations, and we have two unknowns. And our unknowns are T of E1 and T of E2. Our last step is going to be to solve for T of E1 and T of E2, and then write down what A is. In equation 1 up above, we can solve for T of E1. This gives us T of E1 is equal to the vector 1 minus 2 minus T of E2. We're then going to substitute this in into our second equation for t of e1. This gives us 2 times the vector 1 minus 2 minus t of e2 plus 3 times t of e2 is equal to minus 2, 5. We're going to now solve for t of e2, and we have 2 of these. We have 3t of e2 minus 2t of e2, so we get t of e2. And then let's pull everything else to the right-hand side. So we already have a minus 2, 5, and we're going to subtract a 2 times 1 minus 2. Combining these two vectors, we'll have to squish it in here. We end up with a minus 4 for our first component and a 9 for our second component. Now we have t of e2, and we need to find t of e1. We're going to take our t of e2 and plug it back into this first equation. This gives us t of e1 is equal to 1 minus 2 minus our t of e2, which is minus 4, 9, and this gives us a final answer of 5 minus 11. Hang with me, we're almost done. Our matrix A, which is what we want to find, is t of e1 and t of e2. We know what these are now, so we can just write down that A is equal to t of e1, which is this vector, and then t of e2, which is this vector. Let's highlight this final answer. This matrix A is the matrix that determines how u and v are transformed and then can be used to find out how other vectors under this linear transformation are transformed. Let's now look at our last example. In this example, we're given the transformation of a vector u, the transformation of a vector v, and then we're asked to find the transformation of another vector, which we'll call w. Let's go ahead and label our vectors. Our first vector is going to be vector u, and our second vector is vector v, and then the vector whose transformation we want to find, we'll label w. Let's go ahead and label t of u and t of v. So the 1 minus 2 is our t of u, and the minus 2, 5 is our t of v. It always helps to label the vectors. Before we begin, I want to compare this example to the last example. If we needed to find the transformation of a lot of vectors in addition to vector w, we would first need to find A like we did in example 2. Since in this problem we're only asked to find the transformation of one vector, and that's vector w, we're going to use an easier method. I've broken down this method into 2 steps that we can follow. Our first step is that we're going to write w as a linear combination of u and v. The idea behind this is if we know how u and v transform, we can write w as a combination of u and v and then find how w transforms. We'll write that w is equal to c1 times u plus c2 times v. Let's now plug in our vectors. Our w is 1, 2, and that's equal to c1 times our u, which is vector 1, 1, plus c2 times vector v, which is 2, 3. We now need to find c1 and c2. To find c1 and c2, we're going to place vectors u and v in a matrix that's augmented with w, and we're going to put that matrix in reduced echelon form. Our matrix looks like this. We have 1, 1, 2, 3, and we'll augment that with our vector w, 1, 2. I'm going to skip the steps. It's actually only one step that I'm skipping. And here's what we end up with. Our matrix looks like 1, 0, 0, 1. And on the right-hand side, we have a minus 1 and 1. If we circle our pivots, we can see that C1 is minus 1 and C2 is equal to 1. We can now write W in terms of U and V. We have our vector W, 1, 2, is going to be minus 1 times our vector 1, 1 plus 1 times our vector 2, 3. In the second and last step, all we have to do is compute T of W. Our T of W is just our transformation of our vector 1, 2, and taking the transformation of both sides of this equation, we get that this is equal to minus the transformation of 1, 1 plus the transformation of 2, 3. We have to look back up above to see what these transformations are equal to. The transformation of 1, 1 is 1 minus 2, and the transformation of 2, 3 is minus 2, 5. Let's go ahead and plug those in. This gives us a minus the vector 1 minus 2 plus the vector minus 2, 5. And this is equal to the vector minus 3, 7. Let's highlight this final answer. This example shows us that if we know how two vectors transform, we can use that information to find how another vector transforms under that linear transformation. Be sure to check out the next video in this series, where we'll learn all about reflection, projection, rotation, contraction and expansion, and shear transformations.
If this video has been helpful to you, please consider subscribing to my channel. Keep believing in yourself and have a great rest of your day.